Well, in the next, let us talk about entropy, the measurement of information, or the measurement of uncertainty in a system. Why in a data modeling subject we need to consider how to measure the amount of information. This is because we want to build automatic question asking and answering system so that it can remove the uncertainty about the target value by asking questions about the observed value. So you might want to check the previous discussion about the motivation. Uh, to build a system to remove certainty, in the first place, we would like have some measurement of the uncertainty. So that is why we need to study the measurement of information. Consider any kind of uncertainty, maybe the simplest, most straightforward, uncertain system at all. We have two marbles of different colors, red and green. Then we take one marble randomly. We don't know which color it is, and the taken out marble's color is of our interest. This is the simplest uncertain system that could be. So if it is not completely surprising if I'm telling you that, well, if you want to, if I allow you to ask one question and one question only, for which I only answer yes or no, such a closed binary question, you would be able to figure out what color it is in the marble that has been taken from this stochastic system. Not surprising? Okay, then let us build a little bit more complexity in the system. How about if our system have 4 events? Say those marbles all have the same probability, the same likelihood of being taken out as the outcome of our experiment. In this case, how many questions? How many yes, no closed questions, binary questions, one need to ask to figure out what the color of the taken out marble? Before you jump to the answer, try to consider I'm asking you to build a question and answer system. One thing must be taken into account is system has to be built before you have done any experiment. You cannot change the strategy of asking questions after the experiment starts running. And importantly is because this is an uncertain system, we are concerned with the average number of questions you need to ask. For example, if you have designed a system of asking questions, we don't judge the efficiency of the system by using the system to figure out one marble color. We might want to repeat the experiment 10,000 times and take the total number of questions that's been asked in this experiment and divide its number by 10,000 and take the average queries that is needed. So you might feel the impulsion to ask a simple question like that. Is the marble red? Maybe when you get the answer no, unfortunately. So you might ask, is the marble green? No. And then you carry on the guessing, is that blue? Well, you get the answer yes. So on and so forth. Okay. Then if you keep asking questions like that, you can estimate how many questions you need to ask to figure out the status, the color of the taken out marble. You have 1/4 of the chance to hit the color in one question. You have 1/4 of the chance to hit the answer by asking 2 questions. And you have 1/4 of the chance of hitting the answer using 3 questions. And if you are really unfortunate, you get straight 3 no's in the questions. You don't need to ask further questions because now you have already removed all the uncertainty in the system, and you are certain that the color is the remaining one. So you have 1/4 of the chance, another 1/4 of the chance of hitting the answer using 3 questions. So putting them all together, you have 1/4, 0.25 questions, and 0.5 questions, and 0.75 questions, 0.75 questions. You need slightly more than 2 questions to figure out what the status of the marble. So can we improve? Maybe you are clever enough and well, have figured out. We are not limited to construct. Sorry, this should be for outcomes to construct the events strictly according to the outcome. We can combine the outcomes to form new types of events, such as is the takeout marble color red or green? If the answer is no, you can ask, is it yellow? If the answer is yes, you can ask, is that red? So I think you get the point. Now our questioning system, in the first question, we split the status in 2 halves. On the top half, you have red and green. The bottom half, you have golden, yellow, and blue. And in the next question, we pin the particular color. In this way, you can figure out the status of the system in exactly 2 questions, which is a seed from the sequential way of formulating the questions. Okay. Then how about let us make it more complex? Consider 8 events. So instead of coming up a lot of different colors, let me distinguish the new marbles using a skein of, well, maybe not marbles, maybe they are discs. Okay. I put some borders on 4 of the discs so they distinguish from the previous 4. So how to design a system to ask questions and figure out to remove the uncertainty from the system? Maybe it is not very difficult to come up with an idea. You just need to add one more query to figure it out. Is the taken out disk the bordered one or borderless one? Then the situation returns to the previous one. So by adding one more question, you are able to figure out the uncertainty in the system with the number of states doubled. So this intuition points to the direction that the amount of uncertainty that can be removed by n questions should be proportional to something, and that thing is with the growth exponentially to the power of some quantity that with the same magnitude of n. So when the number of questions grows, the the size of the uncertainty system you can figure out grows exponentially, which is good news, which means we can use efficient encoding to to carry a large amount of information. Okay. And that is the very significant breakthrough by Shannon, who did research back to the era of World War II. Then how about uneven probabilities? In the previous examples, we consider all the outcomes will become the outcome with even probabilities. That is called even distribution. But how about if the probabilities are not different? Consider this system. Instead of have the equal number of four colored marbles or discs, now we have half of some discs with the color green, and of the remaining part we have half of them half of them to be blue, and of the remaining part half of them to be green. In and the red and the golden discs are minority. So in this system, how could we design a questioning framework that is most efficiently remove uncertainty? Let me draw an analogy from this system and the previous one. Look, now the information carried by is blue replaces the one that in the previous system has border. So by asking whether the color is blue, you remove half of the uncertainty. This intuition suggests that we should ask the more prominent outcomes first. Therefore, either you hit the right answer or to remove a larger portion of uncertainty from the uncertain space. So if we design questions like, first let's ask whether it is blue. If it's not blue, ask whether it is green. If it's not green, then we distinguish red and golden. In this way, we will have a system of questioning. Averagely, we need this number of questions to get the right color. So with half of the chance, we end up with using only one question. And if the marble is green, and the chance is 0.25, we need two questions. And otherwise, with other colors, each of probability 1/8, we need three questions. Totally put it together, the number of questions needed to clarify the status reduced from the previous two. And that is according to our intuition, because the order to the most orderly status of the system that can have is even distribution. If everything happens with the equal probability, there isn't much information, there's not much knowledge that can help you to prior to make out the state of the system. On the other hand, if the system has some preference, you can take advantage of this kind of prior knowledge and design your questioning system. From now on, I might call that communication system, because this questioning can be considered as you want to deliver, to transmit the status of the system to someone that has not direct observation of the system, but relying on your description to figure out what is the status. So putting everything together, the equation, don't be scared by the term equation of computing. The entropy of the system, this amount of information in the system, is in this way. We take the sum of all possible outcomes, and for each outcome, that is obviously you need to weight the question number you allocate to this outcome using its own probability, and how many answers or how many questions you want the design system to reach that outcome is proportional to is the logarithm with base 2 of the inverse of the probability of this outcome. This is a little bit mouthful. Let's explain that more clearly. If the probability of an outcome is really small, such as 1/8, then its inverse is 8. By 8, if you ask yes no questions, you want to ask 3 questions before you get into this kind of event. On the other hand, if the chance is large, say if it has half of the chance, then its probability is 0.5, and its inverse is 2, and therefore you want to use only 1 question to reach this event, this outcome, and therefore log 2 of 2 is 1. Okay, and you might understand, you might try to consider if for some system that is there is only one possible outcome. See, if this is all blue, then what is the entropy? Well, you have this 1, and this p is 1 because the probability is 1, and 1 inverse is 1, log 2 of 1 is 0. This is very reasonable because you do not need to ask any question if the outcome is known for certain prior you do any experiment. So the uncertainty is 0. This system does not carry any information. This said, you might there is a side question. You might have a doubt that, for example, if you have allocated the events in system very nicely, 1/8, 1/4, half, so that they are all integer power of 2. But how about if we have some events such as this 7/8? You cannot allocate an integer number of questions to that. Okay, the previous calculation of entropy refers to the ideal query system and refers to the asymptotic, that is, you take something to the limit of infinity experiments, this kind of calculation. It can deal with real value quantities. If there is no such implementation, real world implementation of optimal inquiry or encoding system for one event, one experiment, we can combine multiple, even to infinite number of experiment, and do the do the do the encoding or question asking design accordingly. For example, in this system, we might be able to do 5 experiments altogether, and the first question is the outcome are the outcomes of the 5 experiments all blue? And if it's not, maybe the second question is, has the set 4 blues, which summarize 5 different outcomes, say red, blue, 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 red, blue, 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 so on and so forth. And when you put all those kind of calculation all together, the optimal, the as efficient as possible encoding system will give you the certain answer of the system using this number, this length of encoding, the entropy. That is the meaning of the entropy. So summarize, now we have a powerful mathematical tool which allows us to determine how uncertain it is of a system consisting of random events. We will use this concept to measure how uncertain we are of the target value, which is our interest of prediction, after we have performed something.